Alright, so in this video we go over section 3.4 of library of functions and piecewise defined functions. Okay, so first we go over the library of functions. So library of functions, it's a brief summary of the different common functions and their graphs. Typically this comes in college algebra books and even in calculus books as a table, or like that is located in the back or in the first couple pages of the textbook. You know that it's attached to a formula sheet, which is always useful to refer to all of these functions and look at their properties. So in this case, rather than just showing you the graphs, because I could just show you the graph and just use them, well, it's important to look at their properties, and by properties like the ones that we have looked throughout this chapter and also throughout what we have covered so far about this class. Alright, so we have one of the simplest functions, the constant function, whose function is f of x equals to b, where b is any number. We have it right here, f of x equals b, and it's nothing other than a horizontal line. That's all it is, a horizontal line. Alright, so let's look at the properties for this type of function. Okay, so the domain, well, the domain again from the graph, we get it from observing the graph from left to right, and in this case, well, notice this function covers all real numbers, right, which in set notation x such that x belongs to the set of all real numbers, or using interval notation, negative infinity to positive infinity. Those are the two ways to represent the domain of that function. Now, what about the range? Well, this one is a little bit tricky to express, okay, because in this case the range does not even include an interval but only a value. Okay, so the range is just y such that y equals b using set notation. Okay, if we were to express this in interval notation again, well, in this case it doesn't go from some number to another number. It's not an interval. It's just the value b. In this case, this is a special notation called a singleton. That's when it's not an interval, when it's just that value. What about the intercepts? Well, again, there are two intercepts, x-intercepts and y-intercept. In this case, in the x-intercept is the point at which the graph touches or crosses the x-axis, while the y-intercept is the point at which the graph crosses or touches the y-axis. In this case, this function has only a y-intercept. Right, so y-intercept, which is located, it's actually stated here, it's 0, b. The question is the function even or odd? Let's recall the definitions of even and odd. So a function is even, again, if the graph of the function is symmetric about the y-axis, and the function is odd if the function is symmetric about the origin. Again, the parity of a function, it's either one or the other. There's no such thing as a function being being both even and odd. And in this case, if you look at the symmetry, this is symmetric about the y-axis, so the function is even. Okay, do we have an absolute max or an absolute min? Well, in this case, look at the graph. Look at the behavior of the graph. This graph is never increasing nor decreasing, so we can have a max, or decreasing and then increasing, so we can have a min. So in this case, I would just say NA does not apply. In this case, there's no max, there's no min. And because of this, well, there's no intervals in which the graph is increasing nor decreasing. Okay, let's look at the next type of function. We call it the identity function. It's a straight line, it's a diagonal line, but the reason for which we call it the identity function is because if the input and the outputs are the same, for example, if I plug in 0 to the function f of x equals x, the y value is going to be as well 1. If I plug in 1, the y value is going to be 0. For the input 1, the output is 1. For the input 2, the output is 2. For the input 3, the output is 3, and so on. So that's why we call it the identity function. Alright, what about the domain? Okay, unlike the previous graph, well, in this case it was really clear that the domain came from negative infinity and went all the way to positive infinity. When we have graphs in which we have these arrows as part of diagonal lines or curvy graphs, it's not clear in some cases whether it's going flat in a way or it's going infinity in both directions. So the trick here is, what I like doing is break up this arrow into the vertical position and horizontal position, because this diagonal line, for example, this one that goes in the negative direction, when we move in this direction, we are moving backwards and down. When we're moving into this direction, we're moving up and to the right. So these arrows, these horizontal arrows, will help us determine that the domain is again all real numbers, also known as negative infinity, positive infinity. For the range, the arrow pointing down implies that the graph goes down forever to negative infinity and goes up forever to the positive infinity. So y such that y belongs again to the set of real numbers, and in interval notation, negative infinity to positive infinity. Alright, intercepts. Intercepts in this case, well, the origin it's a tricky one. I'm just gonna say 0, 0 is the intercept, and in this case this is both x and y intercept. Okay, because the origin passes through both axes, the x-axis and the y-axis. Is this function even or odd? Well, let's look at the symmetry. So clearly this function, the graph, is not symmetric about the y-axis. However, in this case, this function is symmetric about the origin because we have the point 1, 1. If we change the sign of both numbers 1 and 1, we get -1 and -1, which is a point that also exists on the graph of f of x. So for that reason, the function is symmetric about the origin, which makes it an odd function. Do we have an absolute max or an absolute mean? Well, in this case, the graph increases forever. It never gets flat or never reaches a max to then go downward. So again, in this case, this is not going to apply. It's not going to apply at all. There's nothing. Okay, but now in this case, is the graph increasing or decreasing? Well, in this case, this line is going up forever. So in this case is increasing, and it's increasing in the interval from negative infinity to positive infinity. Alright, let's look at the next type of function. So for the next type of function, we have the square function, the f of x equals x squared. Okay, first of all, let's determine the domain. Okay, again, like I was mentioned earlier in the previous example, we have this arrow, and that arrow as well implying that the graph goes on forever. But in this case, it looks like more vertical than it goes horizontal. That's correct, but still we do that trick I showed you before. This is moving in the x direction, moving in the y direction, moving in the negative x direction, moving in the positive y direction. So when looking at the extension of these arrows, this is telling us that the domain is the set of all real numbers x such that x belongs to all real numbers, or negative infinity to positive infinity. What about the range? In this case, well, so what did we do to find the domain? We basically scanned the graph from left to right, and we found out that the graph goes on from negative infinity to positive infinity. Now, to find the range of the function, we are going to scan the graph from bottom to top, and we are going to look for the lowest value of y and the largest value of y. Here, the lowest value of x, or the smallest value of x, was negative infinity. The largest value of x is positive infinity. Here, the smallest value of y is not going to be negative infinity. In this case, it's going to be the vertex of the parabola for which the y value is 0. I'm going to write that using interval notation first, and then the graph starts extending and going up all the way up to positive infinity. Now, what about the symbol for the 0? In this case, notice the point is defined, the value is defined for that, so we use bracket. How do we use interval set builder notation? So x such that x is greater than or equal to 0. That's how we express it using that notation. Intercepts, do we have any? Well, clearly we have an intercept, and in this case, again, it's both x-intercept and y-intercept. So in this case, it's the order pair 0, 0. Is this function even or odd? Well, look at the symmetry. Again, keep in mind that a function is even if it's symmetric about the y-axis, and it's odd if it's symmetric about the origin. So in this case, we can see the symmetry with respect or about the y-axis, so this function is even. Do we have an absolute max and an absolute mean? Well, so in this case, this parabola has a lowest point, which makes it a minimum, because again, think of the roller coaster as we were using that idea in the previous section. So the roller coaster is going downhill, reaching a minimum point, and then goes up the hill again. Now, what is the coordinate of that absolute minimum? So the absolute minimum is the point 0, 0. Okay. Now let's find intervals in which the function is increasing and then decreasing. So let me write that down. Increasing first, or decreasing first, doesn't matter. Well, I already wrote increasing. Decreasing. Alright, okay, again, I'm going to write minus symbols for the portion of the graph that is decreasing. So in this case, it's decreasing from negative infinity to 0, excluding the 0, because here, exactly where the vertex is, the graph happens to be flat. Okay, so I don't want to go beyond the scope of this, but at this point, if we have a tangent line, the slope is 0, and in this case the slope is negative, and here the slope is positive. Okay, so in this case a graph is decreasing where the slope of the tangent lines are decreasing. But I mean, I don't want to get too technical with this. This is more details about this. You're going to see them when you get to calculus. Okay, so I'm going to use green for, hopefully it's easy to see because the paper is green. This part of the paper is green. So plus, oh, it can be seen. Positive, it's increasing. And it's increasing from 0 to positive infinity. Okay. Now, let's look at another graph, the cube function. Okay, the cube function, it's very similar to that of the square function, except that the first half is not pointing up, but rather is kind of flipped and pointing down. Now let's see. Let's find the domain. Okay, typically when we look at a graph like this, because of how stretched it looks like, and typically we think that this graph only stops at, for example, in this case at -2 and then at +2, but that's not true. Again, this graph is curved, so in this case we're going to use the same trick. Yes, we are going to go down faster than we're going back, just the same way we're going to go up faster than we go forward. So, but still there's movement in both directions, the x direction and the y direction. So these two arrows extending forever in both directions indicate that the domain is the set of all real numbers By the way, before I move on, I've just spotted a silly mistake I made above. So over here I was supposed to write not x for the range, but rather y, because the range has to do with the y's and not the x's. Okay, so here I'm gonna do the same for, let me write this using interval notation, and y such that y belongs to the set of all real numbers. Okay, and same interval notations, negative infinity, positive infinity. Intercepts, do we have intercepts? Yes. The origin again. Is this function even or odd? Well, in this case, look at the symmetry. This function is not symmetric about the y-axis like the parabola from above is. However, in this case, I'm going to apply the other criteria. Is the function symmetric? If the graph of the function symmetric about the origin. So in this case, we have, if I choose this point negative, to choose 1, 1, the point 1, 1, we change the sign of both numbers and we get a point that is also on the graph of that function, then it's symmetric about the origin. So because this function is symmetric about the origin, then it is odd. Absolute max and absolute min, well, in this case it doesn't apply. It's always going up, so it never ceases going up, so not applicable. So increasing, decreasing, well, it is increasing only, and it's increasing in the interval, well, it's increasing forever. It's always increasing, that is from negative infinity to positive infinity. Alright, let's look at the next function, the square root function, which looks like this. Okay, f of x equals the square root of x. Okay, so we're going to do the same trick to find the domain and range. And again, typically because of how this graph is horizontally stretched, that makes us think that the graph only goes on to certain value like this, right? Which actually the formal way to call this tendency is goes asymptotically to some value, but in this case it's not the case for this function. So we use the same trick. We break up this arrow into the horizontal and the vertical one to help us get the domain. Now we're going to scan the graph from left to right to determine the domain, and from left to right the smallest value of x is 0, and the largest value of x this function can take is infinity, goes all the way to infinity. Brackets for the 0 because notice how we have a full bubble, a solid bubble. Writing this using set notation, x such that x is greater than or equal to 0. Okay. So notice I'm using both notation, set notation, because it is very important to be able to describe domains and range using both notation, set notation and interval notation. It's going to depend sometimes in the homework or on a quiz or an exam question what you will be expected to write when you're given a question like this. Alright, so for range we are going to scan the graph now from bottom to top in the vertical direction, and we will find out that the smallest value of y is also 0, goes all the way to positive infinity including the 0. So the range will be y such that y is also greater than or equal to 0. Intercepts we have only one, again 0, 0. Okay, well, you might be thinking, well, are all the graphs having this boring origin as the intercept? Well, for this basic graph that we call the parent graphs or the graphs from the library of functions, yes. But in a further section, actually I believe it's the next section, we're going to go over the different translations and transformations, and everything will be shifted. So we're going to look at all those shifted. That's going to shift domains, it's going to shift intercept, and the fact that if some function that used to be even or odd, there will be no more even or odd depending on the case. Okay, so for now we're going to see all the same origin all the time pretty much. So is this function even or odd? Well, in this case, let's see. Symmetry about the y-axis. Do you see this point reflected on the other side? Well, there's nothing. Do you see this point reflected on that side? Well, there's nothing. So in this case, it's not even. So we can cross that out. What about odd? Is this function symmetric about the origin? In other words, if I change the sign, -1, -1, do we get another point over here? Well, we don't get that either. So in this case is neither. It's neither even nor odd. Absolute max, absolute mean. Well, in this case this graph is always increasing, and it never, we don't ever see this graph going down, so we can have a max, or it's not going down and then going up, so we can see a mean. So in this case it's not applicable, none of them, neither max nor min. But in this case the graph goes up, always goes up. I mean it goes up a little bit steeper at the beginning, but later it kind of starts to chill a little bit, but it's still increasing. It starts increasing at a lower rate than it is at the beginning. So it's increasing, but in this case in the interval from 0 inclusive to positive infinity. Let's look at a few more functions. The cube root function. So the cube root, it's going to look very similar to that of the square root. However, it's going to have another tail in the negative direction and below the x-axis, as opposed to the previous one, which is the square root. Okay, domain. Again, we have this curvy shape. Okay, we need to break this up into two arrows. Okay, so scanning or reading the graph from left to right, we find out that the graph goes from negative infinity, goes to negative infinity in the negative direction and positive infinity in the positive direction. That means x such that x belongs to the set of all real numbers. Interval notation for this, again, negative infinity to positive infinity. The range of this function, look at this arrow pointing down to negative infinity. Look at this arrow pointing up to positive infinity. So that means y such that y belongs to the set of all real numbers, which in interval notation is again negative infinity to positive infinity. Okay, intercepts. Again, the intercept 0, 0, the origin. Okay, what about even and odd? So in this case, the graph is not symmetric about the y-axis. However, in this case, it meets the criteria for the graph being symmetric about the origin, because if I choose again this point, and if I change both the signs of both of them, -1 to -1, it exists on the graph of this function, which makes it an odd function. Absolute max, absolute min. Well, again, the graph is going up, is always increasing. So in this case, we don't have any of this. I mean, okay, increasing, decreasing. Well, the graph, we already said, it's increasing all the time. It's increasing. In the interval negative infinity to positive infinity. Another class of functions, the reciprocal function, f of x equals 1 over x. Well, we call it the reciprocal function because in comparison to f of x equals x, which is the identity function, here we have the reciprocal of the identity, so that's why we call it the identity. Alright, we need to be very careful with this function, especially when it comes to looking at graphs like this from textbooks, or when you graph this function using a graphing calculator, because yes, the graphing calculator is a very smart device. However, it's not that smart as you think, because number one, for this graph we need to make an extension of its tails. Okay, this graph is going to go forever like this. Okay, it's going to go in. So it's going to get closer to the axis. And also, this function, the graph of this function, has a horizontal asymptote and a vertical asymptote, which actually coincide with the coordinate axis, in fact. However, later on, when we move to the next section, to shiftings and translations and transformations, so we're gonna have a function like this, but move 2 units to the right and then 1 down, etc. Also, these asymptotes will be moved, but the thing is, when you graph this using your TI calculator, your calculator will never display this asymptote. So that's a little caveat about depending too much on the graphing calculator. So it's very important to know this, to keep in mind these properties, which in this case are this asymptote. So the domain, all right, in this case the domain, So this indicates that the graph goes on forever. In this case, it's fine to take just the horizontal arrow, because as opposed to the previous graphs, in this case this is approaching the y value equals 0 asymptotically, and same here, it's going down to the negative infinity and positive infinity, positive infinity. So the domain, we need to be careful here. I know what you're thinking. Well, we're scanning the graph, goes from negative infinity to positive infinity. Yes, it goes from negative infinity to positive infinity. In other words, all real numbers except 0, because that's the location of the vertical asymptote for this graph. So the domain, it's going to be using set notation x such that x not equal to 0. So in this case, we're saying here that x can take any value except x equals 0. How do we express that using interval notation? Yes, negative infinity to 0, and then with the union symbol, 0 to positive infinity. For the range, if you scan the graph from bottom to top, you will find out the same thing. It's going to come from negative infinity to positive infinity. In other words, all y values, all real numbers in the y direction. However, the graph is going to get interrupted by this horizontal asymptote occurring at y equals 0. So y such that y cannot be a 0. In other words, in interval notation, negative infinity to 0, union to 0 to positive infinity. Intercepts, in this case, if you look at this graph, is not intersecting at any point at all. So intercept known, we just say, is this function even or odd? Well, look at the symmetry here. Use these asymptotes to look at the symmetry. So the vertical asymptote, we don't have any graph to the left that is actually reflecting these points, right? So in this case, this graph fails to be even because it's not symmetric about the y-axis. However, let's take a test point again, our favorite 1, 1, and change the sign of both numbers. Did you get a point when you change the sign of both numbers? Did you get another point that it's also on the graph? In this case, yes. So that's why this function is symmetric about the origin. Hence, it's odd. Do we have a max? Do we have a min? Well, in this case, we don't have max and mins. None of them. And what about this function? Is it increasing or decreasing? Well, be careful, because again, when we look for increasing, decreasing, we scan the graph from left to right. So here it's going down, and it also is going down here. So the graph is decreasing. The function is decreasing in the interval comprised by negative infinity to positive, to 0, with a union symbol, 0 to infinity. Okay. Again, yes, it looks like it's going up here, but that happens when you look at the graph from right to left. But that's not the right way to look at graph. It's always from left to right. Alright, let's look at the last type of functions. At least as far as the ones cover within the scope of this course. There's some more functions that we're going to look later, like the logarithmic functions, the exponential functions, and in future courses you're going to look at the trigonometric functions, sine, cosine, tangent, etc. And they also have their own very, very interesting properties. So we are going to finish this topic by looking at the absolute value function, which is very recognizable by these absolute value bars surrounding the letter x, the variable x. Alright, so let's find the domain. Again, we're going to use the same trick. In this case, the extension of these arrows tells us that the domain is all real numbers. There's no interruptions, right? Like in the previous graph, there was an interruption here due to the vertical asymptote. But in this case, for the absolute value function, we don't have that asymptote. So x belongs to the set of all real numbers. Using interval notation, this is negative infinity to positive infinity. The range of this function, what's the range of this function? In this case, we are going to scan the graph from bottom to top, and note it has a very similar shape to that of the parabola, like I believe it was like the third one we analyzed here. So the range is y, not x, y such that y is greater than or equal to 0, because 0 is the lowest value, and on all numbers greater than or equal 0. So in this case, bracket 0 to positive infinity using interval notation. Intercepts. Do we have any intercept? Come on. No, again, the 0, 0. Yes, the 0, 0. Again, like I mentioned before, we are going to shift and translate this function, strings, mash, and we're going to do a lot of interesting things to these functions in the next section. Okay, even or odd. Well, in this case, the graph is symmetric about or with respect to the y-axis, so this is even. Do we have an absolute max or an absolute min? Well, we don't have an absolute max, but we have this absolute minimum point, which in this case is the origin again. Is it increasing, decreasing? Do we have intervals in which it's increasing and decreasing? Yes. Decreasing within the interval from, decreasing in the interval negative infinity to 0, and increasing on the other hand in the interval from 0 to positive infinity. Alright, and with this function we finish this topic, this topic for this section. Now the next topic for this section is to graph and analyze piecewise-defined function. Alright, what about piecewise-defined function? Well, in this case, we know a function is defined piecewise when it's when we have different equations with certain restrictions or conditions. Okay, so we're going to graph. Actually, we're going to graph both two functions in this case in the same graph, but with some limitations. Well, let's see. So, for example, if we were to graph, the function, let's say, let me get some. I'm just looking for a pencil. I don't have a pencil, but I have a lead here because I will need to erase. So, if we were to graph x plus 3, here we would go to the y-intercept, which is 3, and then we do the rise over run 1 over 1. And then rise 1, run 1, rise 1, run 1. And we will have this graph. We will have a diagonal line covering, going all the way from negative infinity to positive infinity. However, in this case, we are not going to draw the entire graph, because for x plus 3, I have this condition here, which is x less than negative 2. That means the OK inputs for the first part of the piecewise function, it's all numbers that are less than negative 2. So -2 exclusive, -3, -4, -5, etc. Okay, so how are we going to graph this function? So, okay, I'm going to make a table. I'm going to make a table of values. Okay, I'm going to use blue for x plus 3. Okay, I'm going to use blue. So, but in this case, I cannot take just any value of x. The condition clearly here states that we can only feed the x plus 3 with numbers that are below -2. So -2, -3, -4, etc. Of course, I'm not going to write a million values here. Just a few are good enough. Okay, so I'm going to go y equals -2 plus 3, which is 1, -3 plus 3, which is 0, and then -4 plus 3, which equals -1. I'm going to do one more just to display. Maybe I'm going to go lower. How about -7? -7 plus 3, that's going to give me -4. Okay, so this will give me the order pair -2, 1, -3, 0, -4, -1, and -7, -4. I mean the usual plug-in points, and then plotting the graph. I mean plotting graphing functions or graphing equations by plotting points. I mean by plugging in numbers. All right. So we need to be very careful, because what was the first value that we plugged in? We plugged in for x equals -2. However, notice -2 is not. It's actually excluded because it's only x less than, not less than or equal. Had we had the equal, we would have been okay to plot that point. So in this case, to indicate that I'm not going to really plot this point, I'm going to use this purple color, this pink color. Okay, I'm going to use that to say no, we don't graph it per se. Okay, so what are we going to do? So at the point -2, 1, so -2, 1, I'm going to draw an open bubble. That's how we interpret that, an open bubble. And then -3, 0, and then -4, -1, -7, -4, and then we draw a line. Okay, so that's the first part of the piecewise function. Notice you can still see what I did in pencil here. So in this case, we are not drawing the entire graph. Now let's look at the second part of the function, -2x minus 3. And I'm going to use a different color for that. I'm going to use this, and I'm going to use green. So x and y equals -2x minus 3. Okay. So in this case, if we look at the condition, we can plug in the x values that we can plug into this part of the function is all values that are greater than or equal, in this case -2. So notice I'm plugging -2 to both of the pieces, but in one case, in this case, it's excluded. In the other case, it will be included. So -2. Well, I guess I'm going to skip a few, 0 and maybe 3, and then maybe 4. I don't know. Okay, so y will be -2 times -2 minus 3. Y equals -2 times 0 minus 3. -2 times 3 minus 3. And y equals negative 2 times 4 minus 3. Simplifying these, we get negative times a negative is positive. 4 minus 3, that's 1. 0 minus 3 is negative 3. Negative 2 times 3, that's negative 6. Minus 3, that's a negative 9. Well, we may not get enough graph to plot this point. Okay, so and then this is gonna be 8 plus negative 11. I guess I should take maybe, well, I'll find out what we can take. So this will give rise to the following order pairs. And in this case, it's going to be the point negative 2, 1, 0, negative 3, 3, negative 9, and 4, negative 11. Of course, we're not going to have enough graph to plot these 2 points. So in this case, when I look at this, at this point, because negative 2 is actually an okay input here, it's included, so I'm going to use green to highlight, and I'm going to go negative 2, 1, but in this case I'm going to have a solid bubble, and then 0, negative 3, and then 3, negative 9. Well, in fact, it would be maybe somewhere here. Let me do, instead of 0, let me do, how about 2? Y equals to negative 2 times 2 minus 3 equals, that's going to be negative 7 actually. And then just connect the dots. So in this case, well, this solid point fills in the open bubble from the previous part. Now we're going to use the graph of this graph and the conditions to answer the following questions. Well, f of negative 2. So in this case, we cannot just plug in negative 2 to just any of these two. We need to determine where is this negative good at. Can we plug in negative 2 at the blue, or can I plug in negative 2 at the green? In this case, it is okay to plug in negative 2 at the green one. So in this case, well, we already have negative 2. We calculated it here. So in this case is 1. And then f of 4. Well, f of 4, well, I'm glad I did the calculation here. So it's a negative 11. Notice I'm using the colors, the same colors, in order to honor the corresponding parts of the piecewise defined function. Now, what about f of negative 4? In this case, it corresponds to the blue part of the graph. I'm going to use blue this time. And the y value, or f of negative 4 in this case, is negative 1. It's right there as an order pair from the calculation, or you can see it from the graph. The domain of this function, well, in this case, if you do the trick again, negative infinity, go down to negative infinity, positive infinity, negative infinity. So the domain is the set of all real numbers in this case. Negative infinity to positive infinity. Or in set notation, again, x, such that x belongs to the set of all real numbers. Oops, I didn't. Okay, what about the range? What about the range? So the range, be careful here. So we're going to scan the graph from bottom to top. This arrow indicates it's going to go all the way to negative infinity. However, when we go up, we are going to stop at the highest y value, which in this case is positive 1. Okay, so in this case, using interval notation, negative infinity to positive 1 inclusive for the 1. Using set builder notation, well, actually y is such that in this case y is less than or equal positive 1. In other words, all the y values that are less than or equal 1, as we can see from the graph. And this finishes this exercise. Let's do a couple more. So we're going to look at this function 2 minus x and look at this restriction. So as opposed to the previous restrictions from the previous example, we have values that are less than -2. That means infinitely many values, but in this case it's more restricted. It's more restricted from -3 to 1 only, exclusive for inclusive for -3 and exclusive for 1. And it's also exclusive for 1 for both. Alright, so let's see. I'm going to use x equals, I'm going to use blue again for the first part, 2 minus x. Alright, but in this case, again, I cannot just choose any value of x as we usually do, because again, if we get too technical and if we focus only on 2 minus x, this is pretty much a polynomial function, and the domain of a polynomial function is a set of all real numbers. That is, we can plug in any number at will. However, in this case we have this restriction and we can only plug in numbers from -3, -2, -1, 0 and 1. Okay, so let's plug in these numbers and get the answers. Y equals 2 minus -3, which is positive 3 plus 2 equals 5. Y equals 2 minus -2, that's a 4. Y equals 2 minus -1, that's going to be positive 1 plus 2 equals 3. Y equals to 2 minus 0 equals 2. And y equals 2 minus 1, that's 1. So the corresponding ordered pairs here are -3, 5, -2, 4, -1, 3, 0, 2, and 1, 1. Now we need to be careful about the endpoints here. So because of this because of this less than or equal symbol, the equal implies that we are going to have a full bubble, solid bubble at that point. Because of this less than only, it doesn't have the equal. This is going to be a solid bubble, an open bubble. So in this case, let's see, where's my green marker? Oh, it's right here. It is okay for this to draw a solid bubble, but in this case it's not going to be okay for this value at 1. Okay, so in this case, -3, 5, full bubble, and then -2, 4, -1, 3, 0, 2, and then 1, 1. At 1, 1, we are going to have an open bubble. Okay. Now let's grab the second part of the function comprised by square root of x. And in this case, we can plug in just any value greater than 1. So in this case, x, y equals the square root of x, starting at 1, 2. Well, in this case, I'm not going to use 2. I'm going to choose my numbers wisely in a way that we get exact numbers. So I'm not going to use the number 2. In this case, I'm going to use the perfect squares, like 4 and 9. Okay, that's enough, because in this case I have values of x up to 10, so I'm not going to have the opportunity to have, or the space rather, to have more numbers. So y equals the square root of 1, which is 1. Y equals the square root of 4, which is 2. And y equals the square root of 9, which is 3. That's going to give rise to the following order pairs: x, y. The order pair 1, 1, the order pair 4, 2, the order pair 9, 3. Okay, now let's look at the endpoints. For the point 1, 1, in this case we don't have the equal bar, so it's going to be an open bubble. That is, that point is not defined there. So open bubble at the same location, and then 4, 2, and then 9, 3. So it's going to go like this. Well, the graph is not perfect, it's kind of curvy. Okay. Now let's analyze the function and see what can we answer about it. So f of -2, do we get that from the blue or from the green? In this case from the blue, and the y value, or f of -2, is 4. F of 4, we get it from the green part of the function, which in this case is 2. F of 1. Okay, so at f of 1, what do we have? We have an open bubble. We have an open bubble, and in this case we said it's undefined. It's undefined for 1. The domain. Okay, let's look at the domain. Let's observe the graph from left to right. In this case, notice the full bubble as opposed to this endpoint, to this part right here. This graph has only a full bubble. It's not indicating it's going forever. So the smallest value of x is -3. And then we scan the graph from left to right, but we are going to get to this hole that we need to exclude. The hole is located at 1 union 1, and then in this case this graph is going to go on forever to infinity, and in this case with bracket. What about the range? So for the range, we're going to scan the graph from bottom to top. Alright, I mean, here in this case it's not really easy to see. I mean, the graph didn't come out perfect, but it's going to increase in both directions. The x direction and the y direction is going to go up forever. So the lowest point, which is -1, and then goes all the way up to positive infinity. But in this case, with the caveat that at 1 the function is not defined, it doesn't touch, it's negative infinity. I mean, it's 1 to positive infinity. Alright, how do we express this using set notation? So x such that, well, in this case I'm going to put an x in the middle. X is greater than or equal -3 and less than 1, comma, the other restriction, x greater than 1. On the other hand, the way we express this using set notation, y such that y is greater than 1, not greater than or equal, only greater than 1. Okay, let's do another example, another interesting one example that has, it looks a little bit crazy, it has more parts. Okay, but don't let this scare you. Don't let this scare you, because look at all these restrictions are very I mean, no, without sounding redundant, are very restrictive. So it's going to simplify a lot of the calculations. I'm going to go with the first part using blue. X and y equals x squared. Can I choose any value for x? Well, look at the restriction. I can only choose from 0, 1, and 2. That's it. So y equals 0 squared, which is 0. Y equals 1 squared, which is 1. And y equals 2 squared, which is 4. So this is going to give rise to the order pairs x of the form xy, which are 0, 0, 1, 1, and 2, 4. Okay. Now, let's observe the endpoints of the restriction. There's no equal sign. There's no equal sign here. Only less than. Only less than. That means full open bubble. I mean open bubble and open bubble. So let's graph the function. Let's graph this one. Okay, so the origin will have an open bubble, and then the point 1, 1, it's going to be fine, and then the point 2, 4 is going to have an open bubble, an open circle. And I'm going to graph this part of the parabola like this, okay, with open circles. Okay, let's look at the second part of the function, for which x can be, again, not just any number. Y equals x plus 2. So I'm going to choose values from 2, 3, 4, and 5. I'm just going to skip a few. 2, I'm going to go all the way to 4, and then 5. I mean, it's a linear equation. It's going to be a straight line. So no need to do all of them. So y equals 2 plus 2, which is 4. Give rise to the point 2, 4. And then we're going to have y equals 4 plus 2, which equals 6. 5 plus 2, which equals 7. So in this case, we have the points 4, 6, and 5, 7. So let's plot these points, but let's be careful first about the nature of the endpoints. In this case, again, we do not have the equals, so we're going to have open bubble and open bubble for both endpoints. So open circle here, it's not going to fill in the discontinuity, and then 4, 6, and then 5, 7, but over here we also have an open circle. Alright, what's next? Okay, so in this case I'm going to use a different color. I'm going to use orange. So in this case, for the third part, what are we going to have? We're going to have f of x equals to 7 for x greater than or equal 5. In other words, we're going to have y equals 7, which is no other than horizontal line. Again, it's a constant function like the first one we looked at the beginning of this video, of this section. And in this case, well, look at the restriction. It includes the 5. So in this case, we're going to have, if we were to draw a horizontal line, of course, we're not going to draw the entire horizontal line. So it's going to have a full bubble here, which is going to fill in the discontinuity. and it's going to go on forever. Alright, and possibly the trickiest part about this type of functions, well, let me write it down with a different color. I'm going to use, maybe, I'm going to use pink. So, and I'm going to write it down here. F of x equals 5 when x equals 2. This is simply a fancy way to write another ordered pair in which x equals 2 and f of x, which is y, equals 5. So we are going to have this 2, 5 as a point in the middle of nowhere. Okay, it's not filling in the discontinuity, but the function is still defined in there. All right. Now let's answer the questions here. F of 3. What am I going to use for f of 3? In this case, am I going to use the blue, am I going to use the green, or am I going to use the orange? Well, if we look for number 3 extended, we're going to use the green part. So f of 3, that's going to be from the graph equals to 5. F of 1, what are we going to we're going to look at f of 1. In this case, it's the turn of the blue part of the graph. F of 1 equals 1 from the graph. F of 2. F of 2, be careful, because in this case, the first part for the quadratic involves in a way the number 2. However, there's an open bubble, which means it's not defined. For the second part, which is the green part, involves the positive 2, however, as well as an open bubble. So in this case, we're not going to use that part now. F of 2 is the point that we came up here with pink, which in this case, we're going to answer the question by using the pink part of the function, which is 5. F of negative 2. What about f of negative 2? Well, in this case, the graph has nothing for negative values. So in this case, the function is undefined. For x equals negative 2. What about the domain? Well, let's see. If we look at the domain, we are going to scan the graph from left to right, and the graph starts at 0, yes, but without including the 0 because we have open bubble. And in this case, even though we have this open bubble, well, the graph is discontinuous at x equals 2. However, it's still defined, maybe somewhere outside of the curve or the line, but it's still defined as a point in a way in the middle of nowhere, using quotation marks, because it's not really in the middle of nowhere, it's an actual point, it's a defined point. So the domain, if we keep moving, there's no more discontinuities. Okay, so in this case, the domain will be from 0 to positive infinity in both cases, exclusive for both. Finally, let's find the range. Let's scan the graph from bottom to top. Okay, so from bottom to top, we're going to go from 0 to the first discontinuity, which is at 4, and then from 4 to the highest value of y, which in this case is 7. In this case, it doesn't go on forever in the vertical direction like other graphs did in the previous examples. So the way we define this range, it's going to be from 0 exclusive to 4, union from 4 to 7. How do we express this using set notation? X such that x is greater than 0. On the other hand, y such that y is greater than 0 and less than 4, exclusive, and then y goes between 4 and 7. Alright. And the last example, just to wrap up this section, now we're gonna do the backwards type of problem, in which now we are given a piecewise the graph of the piecewise function, and then they're asking us to write the definition of the function. Alright, notice we have two straight lines, one straight line here and another one there. Okay, let's recall what do we need to get the equations of two lines. We need two pieces of information. Number one, a point, and the other one, the slope. So two pieces of information, and in this case they're giving us 2 points. That's enough information to find the slopes. Okay, so for the first one, okay, it's going to be, the slope will be x2, y2, x1, y1. So the slope, which is y2 minus y1, which is 2 minus 0 over x2 minus x1, 0 minus negative 1. Careful here. So here we're going to have some smile rule. Okay, smile, be positive, 0 plus 1, 2 minus 0 is 0, 2 over 1, which is 2. So now that we have the slope, we are going to use this slope in any of these 2 points. I'm going to use the 0, 2. I'm going to use the point slope form, y minus y1 equals m times x minus x1, where x1 and y1 are the coordinates of the point that I'm going to choose, which in this case is y minus 2 equals m, which is 2, times x minus x1, which is 0. So we're going to have y minus 2 equals 2x, 2 times 0, it's just going to be 0, and all we do is add 2 to both sides to get y by itself. Okay, so that's one. So it would be a good idea to start defining the function as f of x equals, number 1, 2x plus 2. Now we need to find the piece for this other function. Okay, we will look at the restriction afterwards. So now for the other part of the function, I'm going to find the slope between these 2 points. Okay, so in this case, m, which is going to be y2 minus y1, that's 2 minus 1, over x2 minus x1, that's also 2 minus 1, which is 1 over 1, which reduces to 1. And then I'm going to use again the point slope form. And I'm going to choose just any point. I could use 2, 2 or 1, 1. I'm going to use the one with the smallest numbers. All ones. Okay, the slope is also 1. And y minus 1 equals x minus 1. And then when we add 1 to both sides, This is y equals to just x. Oh, interesting. Do you recognize this function? Isn't that just the identity function? Maybe you can see it from here. You can spot that from there. I mean, you can, if you feel comfortable and if you think it's clear for you, go ahead and think, okay, 1 1 2 2 0 0 3 3 and 49 49. That's clearly the identity function. If for some reason it's not clear for you and if you prefer to do what I did here, that's fine. That's actually good to practice material cover in the previous chapter, which is equations of line. It's always good to review those topics whenever possible. So in this case, we're gonna have y equals x. Otherwise, I mean x, f of x equals x. Now it's time to add the conditions for each. Okay, notice that the first diagonal line goes from -1 to 0. On both endpoints, we have solid bubble. So in this case, it goes from -1 to 0. Because they're solid points, we have the equal part of the inequality. On the other hand, for the second part of the function, it has an open bubble at 0 and goes all the way to positive infinity as indicated in this arrow telling us that goes on forever. So the way to write that using a condition x greater than 0, and that's what they were asking us for. Okay, so this is the end of this video, so I'll see you in the next topic.